very, very similar to an AIME 2005 competition problem. Now this one's a little bit of an extension of that, but the question is how many natural numbers or positive integers have exactly 7 proper divisors satisfying this condition that each of the 7 proper divisors is strictly less than 78. Now, again, they use the terminology proper divisor. Just an example of what that means is like, for example, 6 has proper divisors 2, 3, and of course 1. 1's a proper divisor of any natural number. Now notice that 6 gets left out. So again, 2, and that's a 3 there, folks. 2, 3, and 1 are considered proper divisors of 6. 6 is a divisor of itself, but it's not considered to be a proper divisor. So just that's the distinction on the proper. Now, let's take a look here. As far as I can tell, and this is more or less corresponds to the solution of the original problem. There's two mutually exclusive cases, case 1 and case 2 right here. Now, any p for any p, p raised to the 7th has 7 proper divisors, and because of just the uniqueness of the prime numbers, you can list those very easily. 1 is certainly a proper divisor. That would be p to the 0 if you have to know. P to the 1, p raised to the 2nd power, all the way out to p to the 6th. All right. So all these are 7. These are 7 proper divisors, and it turns out 2 is the only one that works. Notice that 2 to the 6th is 64, and that is less than the condition of being less than 78. Now, certainly the others, you would have 2 to the 5th, 32 right here, 2 to the 4th, 16, 2 to the 3rd, 8, and so on. But you can already see that for 3, you're getting way too big. Like, for example, 3 to the 4th would already be 81. Like if we were to allow for the possibility of 3 to the 7th here, one of the divisors of 3 to the 7th would be 3 to the 4th, right? But 3 to the 4th is equal to what, 81? 3 to the 4th is 81. And that certainly exceeds the 78 you see right here. So 2 to the 7th, or 128, is the only only number in this form that would have 1, 2, 3, 4, 5, 6, 7 proper divisors, and also none of the divisors would be larger than 78. Okay. Now, case 2 is slightly more involved. If you take your prime numbers to be R, S, and T, this product has 7 proper divisors, and this is a little bit of a combinatorics problem. There would be 8 total divisors, 2 cubed total divisors, but one of those divisors would be the number itself, RST. So we leave that out, and this is just counting right here. 1's a divisor, RST. Then all combinations of the 2 variables paired together, a little like the elementary symmetric polynomials. But anyway, all 7 of these are divisors. All right. Now, to meet the requirement of being less than 78, you can go no higher than 11 for your prime. 7 times 11 would be 77, right? 7 times 11 would be 77. All other products would be less than 78. Okay. So these are the only primes that would work, and there are 1, 2, 3, 4, 5 of those primes. There are 5 choose 3 equals 10 ways to select any 3 of them. Okay, so we have 1 possibility up here. All right, we have 10 possibilities right here. So overall, that would give us a total of 11 possibilities. There's 11 numbers that satisfy the conditions, and that was the question. They didn't want to know what the numbers were. They just wanted to know how many possible numbers. There's 11 numbers, 11 entire natural numbers that would meet that condition. Again, 1 possibility right here, and then 10 possibilities right here. Now let's just work one of them concretely just to see, so you'll be convinced. Let's just do like 3 times 5 times 7, right? That's a possibility. N is equal to 3 times 5 times 7. So let's write this off to the side here. N equals to 3 times 5 times 7. Okay, now 3 times 5 times 7, what is that? That's 7 times 15 is, what's that, 105? Okay, so 3 times 5 is 15. 7 times 15 is 105. So that equals to 105. All right. So that would be one of the 10 ways to select those 3 primes, right? All right, y'all, that's 105. Okay, again, y'all, hopefully you can see that as a dot, and a dot, 3 times 5 times 7. Again, there's many other ways. There's 9 other ways. We just picked one of those 3 ways. But notice, let's write down the divisors here, okay? We certainly have 1. What else do we have, folks? We certainly have 3. Okay, we certainly have 3. What would be the next one? 5. And y'all, well, all I'm doing is just listing the divisors here. 1, 3, 5. Now the next one, I guess, what order we want? Well, 7, I suppose. Whoops, I lost my marker here. Okay. Okay, so we would have 7, right? And now we have to go through all the products here, right? I guess the first one would be 15. Okay, the next one would be 21. And let's see, the last one would be what, 35? Do we have 7 there, folks? 1, 2, 3, 4, 5, 6, 7, right? And notice that all 3 of these divisors meet the condition of being less than 78. Where you get close is when you're allowing 11 to be one of your selections. But again, this is one of the 10. We use the combinatorics result right here, combination formula, which is 5 times 4 divided by 2, which is 10. And this is just one of them. And there's 1, 2, 3, 4, 5, 6, 7. Hope you guys like that. The competition problem was a larger number. I think it was closer to like 130. So it was kind of hard to, they didn't have time to list any examples. But let me know what you thought about that. And again, it's a slight variation on a 2005 AIME competition problem. All right.